When we speak of particles as the fundamental building blocks of nature, we are not merely repeating a poetic metaphor, we are pointing to one of the deepest discoveries humans have ever made about reality. Richard Feynman often emphasized that what we call things in everyday life are, at a deeper level, arrangements of a very small number of recurring ingredients. The chair you sit on, the air you breathe, the stars in the sky, and even your own thoughts arise from the behavior of these tiny entities. Yet calling them building blocks can be misleading if we imagine them as rigid bricks stacked neatly together. Nature is subtler, more fluid, and far more surprising than that. Historically, the idea that matter is made of small pieces goes back thousands of years. Ancient thinkers guessed that there must be some smallest units beyond which matter cannot be divided. But for most of human history, this was speculation rather than knowledge. What changed in the modern era was not just better instruments, but a new way of asking questions. Instead of asking what matter looks like when broken into smaller pieces, scientists began asking how matter behaves, how it interacts, and what patterns remain the same no matter how deeply we probe. Feynman loved to remind audiences that science progresses not by perfect definitions, but by increasingly accurate descriptions. A particle, in this sense, is defined not by a picture, but by what it does. An electron is not known because we can imagine its shape, but because whenever we set up certain experiments, the same results appear again and again. This repeatability is crucial. It tells us that nature is built from stable elements that behave consistently, no matter where we find them in the universe. At first, atoms were thought to be the ultimate building blocks. Chemistry seemed to confirm this idea. Different substances could be explained by different combinations of atoms, and chemical reactions were rearrangements of these atoms rather than their destruction. But physics pushed deeper. Atoms themselves turned out to be mostly empty space, with tiny nuclei surrounded by electrons. Then nuclei were found to be made of protons and neutrons, and even those were not fundamental. They are composed of smaller entities called quarks. This progressive uncovering of deeper layers might suggest an endless descent, but Feynman cautioned against assuming that smaller automatically means more fundamental. What matters is not size, but explanatory power. The fundamental particles are those that cannot be explained as combinations of simpler things, at least within our current understanding. They are the points where our explanations stop and our rules begin. One of the most striking lessons of particle physics is that diversity arises from simplicity. The entire visible universe can be explained using a surprisingly small set of particles. A handful of quarks, a few leptons like the electron, and some force-carrying particles are enough to account for all known matter and interactions. This economy is not something we designed. It is something nature reveals when we look carefully enough. Yet calling particles objects can quietly reintroduce old misunderstandings. In everyday life, an object has a definite position, a definite speed, and a continuous existence through time. Particles do not obey these rules in the same way. At very small scales, the idea of a particle being here or there becomes fuzzy. Experiments show that particles behave as if they explore many possibilities at once, only settling into a definite outcome when an interaction occurs. Feynman often used the language of probability to explain this behavior. Nature, at the particle level, does not choose a single path in advance. Instead, it assigns probabilities to all allowed possibilities. The particle we detect is not the one that really traveled along a hidden path, but the result of an interference of possibilities. This challenges our intuition, but it matches experimental results with extraordinary precision. Despite this strange behavior, particles remain the foundation of our descriptions of matter. They are the simplest recurring elements in the equations that successfully predict experiments. In this sense, they are not philosophical constructs but practical tools. When physicists say that matter is made of particles, they mean that the best explanations have involved a small set of entities whose interactions account for everything we observe. Another important aspect of particles, as building blocks, is their universality. An electron on Earth is identical to an electron near a distant galaxy. It has the same mass, the same charge, and the same behavior. This universality is astonishing. It means that the laws of nature are not local rules invented separately in different regions of the cosmos, but global principles that apply everywhere. Feynman saw this as one of the strongest arguments for the objectivity of physical law. Particles also blur the boundary between matter and energy. According to relativity and quantum theory, particles can be created and destroyed as long as the appropriate energy is available. This does not mean that nature is careless or random, but that what we call matter is a form of energy organized in specific ways. In high-energy collisions, energy transforms into particles. In annihilation processes, particles transform back into energy. The building blocks are dynamic, not permanent. This dynamism leads to a deeper insight. Particles are not isolated entities existing on their own. They only make sense in the context of interactions. An electron without electromagnetic interaction would be meaningless because its defined properties are revealed only through how it responds to fields and other particles. Feynman stressed that physics is not about cataloging things, but about understanding relationships. The idea of particles as building blocks also helps us understand scale. At human scales, the discrete nature of matter is hidden. Solids feel continuous, liquids flow smoothly, and gases seem like uniform clouds. But at smaller scales, discreteness becomes unavoidable. Heat is explained as the motion of particles. Sound is explained as collective vibrations of particles. Even pressure is the result of countless tiny impacts. The macroscopic world is an average over enormous numbers of microscopic events. From this perspective, complexity is not fundamental. It is emergent. Simple rules governing particles give rise to complex behavior when many particles act together. Feynman delighted in pointing out that there is no special life, force, or mind substance required to explain living systems. The same particles and laws that govern rocks and stars also govern cells and brains. Life is special, not because it uses different building blocks, but because of how those building blocks are arranged and interact. Understanding particles as fundamental building blocks also reshapes how we think about explanation itself. Instead of asking why a table is solid, we ask how the electromagnetic interaction between electrons prevent atoms from passing through each other. Instead of asking why metals conduct electricity, we ask how electrons move through atomic lattices. Each why becomes a how, grounded in particle behavior. Feynman's approach strips away unnecessary mystery while preserving genuine wonder. The universe is not magical in the sense of being beyond understanding, but it is deeply astonishing in how much richness arises from so little. A small set of particles, obeying precise mathematical rules, produces galaxies, mountains, oceans, and conscious beings capable of asking questions about their own origins. In this way, particles are not just building blocks of matter, they are building blocks of explanation. They allow us to connect phenomena across vast differences in scale, from the tiniest interactions to the largest cosmic structures. They provide a common language for chemistry, biology, astronomy, and technology, and they remind us that beneath the apparent complexity of the world lies a deep and elegant simplicity, waiting to be understood. When we continue deeper into the idea of particles as the fundamental building blocks of nature, an important shift in perspective becomes necessary. Feynman often warned that if we cling too tightly to everyday intuition, particles will seem confusing or even contradictory. The mistake is not in nature, but in the mental images we insist on using. Particles are not miniature versions of familiar objects. They belong to a category of reality that demands new rules and new ways of thinking. One of the clearest examples of this is how particles behave when they are not being observed. In everyday life, a stone exists whether or not anyone looks at it. Its position may be unknown, but it is assumed to be definite. At the particle level, this assumption breaks down. Experiments show that particles do not possess definite properties in the absence of interaction. Instead, they exist in a state described by possibilities. This does not mean they are unreal or imaginary. It means their reality is expressed through probabilities rather than fixed attributes. Feynman highlighted that this probabilistic nature does not weaken science. On the contrary, it strengthens it. Quantum theory makes predictions with astonishing accuracy, often agreeing with experiments to many decimal places. The uncertainty is not in the predictions, but in the individual outcomes. When many events are observed, the statistical patterns emerge with remarkable clarity. Nature, it seems, is precise about probabilities, even when it is unpredictable about individual events. Another subtle point about particles as building blocks is that they are indistinguishable in a profound way. Two electrons are not just similar, they are fundamentally identical. There is no hidden label that allows us to track one electron as separate from another. If two electrons swap places, there is no experiment that can detect the difference. This indistinguishability is not a limitation of measurement but a fundamental property of nature. It plays a crucial role in explaining the structure of atoms, the stability of matter, and the behavior of solids. This indistinguishability leads directly to collective effects that would be impossible if particles were distinguishable. The rigidity of solids, the flow of electricity, and the properties of metals all depend on how large numbers of identical particles obey quantum rules together. From simple building blocks arise collective behaviors that seem almost purposeful, yet are entirely the result of impersonal laws acting on countless particles at once. Feynman also emphasized that particles are defined by their interactions, not by internal complexity. An electron, as far as we know, has no internal structure. It does not contain smaller components. Its entire identity is captured by a few numbers, its mass, its charge, and its spin. That such a simple entity can give rise to the richness of chemistry and biology is one of the great surprises of science. It tells us that complexity does not require complex ingredients. It requires the right rules of combination. As particle physics developed, it became clear that not all particles play the same role. Some make up matter directly, while others exist only to mediate interactions. These force-carrying particles are just as fundamental as matter particles, even though we rarely encounter them directly. Their presence is inferred through the forces they produce. This reinforces the idea that particles are not standalone objects, but participants in a web of interactions that defines the structure of reality. The building block picture also reshapes how we think about emptiness. What appears to be empty space is actually a dynamic arena filled with fluctuating fields and virtual particles. Even in the absence of matter, particle-like processes occur. Energy briefly forms pairs of particles that appear and disappear, influencing measurable quantities. The vacuum is not nothing. It is the lowest energy state of a system rich with structure. This realization challenges the naive idea that particles are isolated dots floating in a void. Another key insight is that particles and laws are inseparable. The properties of particles are not arbitrary. They are tightly constrained by the mathematical structure of the laws they obey. Symmetries dictate which particles can exist and how they interact. From this point of view, particles are not independent building blocks, chosen at random, but necessary features of a deeper underlying order. Nature does not merely contain particles. It requires them. Feynman often returned to the theme of humility. Despite the success of particle physics, we must recognize the limits of our understanding. What we call fundamental may one day be explained in terms of deeper principles. History teaches us that today's building blocks were once thought to be indivisible, only to be revealed as composites later. Yet this uncertainty does not undermine the current framework. Each level of description is valid within its domain and extraordinarily powerful in explaining phenomena at its scale. Particles as building blocks also provide a bridge between theory and technology. Modern electronics, medical imaging, nuclear energy, and particle accelerators all rely on precise knowledge of particle behavior. These applications are not side effects, they are direct consequence of understanding how nature is constructed at its most basic level. The abstract ideas discussed in theory become tangible tools that shape everyday life. At a deeper philosophical level, the particle view challenges our sense of permanence. Matter feels solid and enduring, yet at its foundation, it is a dance of entities that can appear, disappear, and transform. Stability is not the absence of change, but the result of balanced processes governed by conservation laws. What seems fixed at human timescales is dynamic at microscopic ones. This perspective alters how we think about change, decay, and continuity in the universe. Feynman's genius was not only in explaining particles, but in conveying why they matter intellectually. Understanding the building blocks of nature is not about reducing beauty to mechanics. It is about discovering a deeper beauty rooted in simplicity and consistency. The same few particles and laws operate everywhere, from the earliest moments of the universe to the present day. This unity suggests that nature is not a patchwork of unrelated phenomena, but a coherent whole. Ultimately, particles as fundamental building blocks offer a powerful lesson about explanation itself. The world is understandable, not because it is simple in appearance, but because complex appearances arise from simple rules. By learning the behavior of particles, we gain the ability to explain an enormous range of phenomena without invoking separate principles for each case. This economy of explanation is one of the strongest indicators that we are on the right track. In the spirit of Feynman, the true value of particles lies not in memorizing their names, but in appreciating what they represent, a successful way of talking about nature that connects observation, mathematics, and imagination. They remind us that reality is far stranger than common sense suggests, yet far more orderly than chaos would allow. From these tiny building blocks emerges a universe capable of producing stars, life, and minds curious enough to ask how it all works. When Richard Feynman spoke about fields and interactions, he was inviting us to abandon one of the most deep-rooted habits of human thinking, the idea that objects act on each other across empty space by some mysterious push or pull. In everyday life, forces feel direct. We push a door and it moves, we pull a rope, and something follows. It is tempting to imagine that particles behave the same way, tugging on one another from a distance. But physics reveals a more subtle and far-reaching picture, one in which fields are the true state of reality, and interactions are the fundamental events that give particles their meaning. A field is not a material substance in the ordinary sense, yet it is not an abstract idea either. It is something that exists at every point in space and time, capable of carrying energy, momentum, and information. The temperature of a room is a simple example of a field. Every location has a value, even if nothing visible marks it. In physics, electric and magnetic fields play a similar role, assigning properties to every point in space. What Feynman emphasized is that particles do not act directly on each other. They interact with fields, and those fields, in turn, influence other particles. This shift in viewpoint solves a long-standing puzzle. If one particle suddenly changes its motion, how does another particle know about it instantly? Classical thinking struggled with this question. Fields provide the answer. Changes propagate through fields at finite speeds, respecting the limits set by nature. There is no need for instantaneous action at a distance. Interactions are local, occurring where particles meet fields, point by point in space and moment by moment in time. Feynman often pointed out that fields are more fundamental than particles because particles can come and go while fields persist. An electron can be created or annihilated, but the electron field remains. A photon is not a tiny bullet of light traveling through emptiness. It is a ripple in the electromagnetic field. This perspective reframes particles as events or excitations rather than permanent objects. What we call a particle is the smallest possible disturbance that a field can support. One of the most powerful consequences of this idea is that it unifies matter and forces. In older pictures of physics, matter was made of particles and forces were separate entities acting between them. Field theory erases this division. Forces are simply interactions between fields, and particles are manifestations of those same fields. Matter and force are no longer opposites. They are expressions of a single underlying framework. At the quantum level, fields behave in ways that defy classical intuition. They fluctuate even in their lowest energy state. What we think of as empty space is actually filled with restless activity, with fields constantly vibrating. These fluctuations can have measurable effects, influencing particle behavior and even altering the energy of systems. Feynman emphasized that this is not philosophical speculation but experimentally confirmed reality. The vacuum is alive with structure. Interactions in this framework are not smooth, continuous processes, but discrete events. When two electrons repel each other, they do so by exchanging disturbances in the electromagnetic field. These exchanges can be represented as particle-like entities, such as photons, but these are bookkeeping devices that help us calculate probabilities. What truly exists are the interactions themselves, governed by precise mathematical rules. Feynman diagrams, which he famously developed, are visual tools for tracking these interactions, not literal pictures of what happens in space. A crucial insight from field-based thinking is that particles cannot be fully understood in isolation. An electron without an electromagnetic field would be meaningless because its defining property, electric charge, is expressed only through interaction. Fields give particles their identity. Mass, charge, and spin are not intrinsic labels glued onto particles. They describe how particles respond to fields and how they influence fields in return. This relational nature of reality marks a deep departure from everyday thinking. We are used to describing objects by listing their properties. Field theory encourages us to describe objects by how they interact. To know what something is, we observe what it does. This operational viewpoint aligns perfectly with Feynman's broader philosophy of science. Understanding comes from behavior, not from imagined pictures. Fields also impose limits and rules on interaction. Conservation laws, such as the conservation of energy and momentum, are built into the structure of fields. When particles interact, these quantities are not optional, they are enforced automatically by the underlying symmetries of the fields. This means that interactions are not arbitrary events but constrained processes that fit into a larger, coherent order. The idea of fields reshapes our understanding of causality. Causes do not jump instantaneously from one particle to another, they propagate through fields at finite speeds. This respects the structure of space-time itself, as described by relativity. Fields live in space-time, and their behavior is inseparable from its geometry. Feynman delighted in showing how seemingly different concepts, forces, particle, space, and time interlock into a single, consistent picture. At larger scales, fields explain familiar phenomena in a unified way. Light is an oscillation of the electromagnetic field. Radio waves, microwaves, infrared radiation, visible light, and X-rays are all the same kind of field behavior, differing only in frequency. This continuity across scales highlights the power of field theory. It connects the everyday and the exotic without changing the underlying principles. Perhaps most striking is how fields account for stability. Why does matter not collapse under electric forces? Why do atoms have specific sizes and shapes? The answers lie in the balance of interactions mediated by fields. Stable structures emerge when field interactions reach equilibrium. What appears solid and permanent is actually a dynamic balance of forces at the field level. Feynman was careful to stress that fields are not optional theoretical inventions. They are demanded by experimental evidence. Whenever scientists try to remove fields from their descriptions, contradictions appear, predictions fail, and consistency is lost. Fields are not added to physics for elegance alone. They are required for correctness. Understanding fields and interactions also prepares us for deeper questions. If fields are fundamental, where do they come from? Why do they have the properties they do? Modern physics suggests that fields themselves may arise from even deeper principles such as symmetry and geometry. While these questions remain open, the field-based framework has proven extraordinarily successful, guiding decades of discovery and technology. In Feynman's view, the greatest achievement of field theory is not that it gives us a final answer, but that it gives us a reliable way to ask questions. By focusing on interactions rather than objects, it keeps physics flexible and responsive to new evidence. It reminds us that nature is not obligated to match our intuitions, only to follow its own rules. Seen this way, fields and interactions are not just technical tools. For physicists, they are a new language for describing reality. They teach us that the universe is less like a collection of solid things and more like an intricate web of relationships, constantly in motion. Particles appear, interact, and vanish, but the underlying fields persist, shaping every event. This perspective, championed so clearly by Feynman, reveals a universe that is deeply interconnected, profoundly dynamic, and astonishingly coherent. Continuing this exploration of fields and interactions, it becomes clear that one of their most profound implications is how they redefine the concept of cause and effect. In everyday thinking, causes feel immediate and localized. One object strikes another, and the result follows. At the level of fields, causality is distributed. An interaction is not a single moment of contact, but a chain of influences spreading through space and time. A particle disturbs a field, that disturbance propagates, and another particle responds. Cause is no longer a point-like event, but a process unfolding within a continuous structure. Feynman emphasized that this view removes much of the mystery surrounding forces. Instead of asking how one particle can mysteriously influence another across empty space, we recognize that there is no emptiness at all. The field is always present, carrying the influence forward. This perspective restores locality to physics. Everything that happens at a point is determined by what is happening in its immediate surroundings, not by distant objects acting magically from afar. Fields also explain why interactions have characteristic strengths and ranges. The electromagnetic field extends infinitely, which is why electric forces can act over large distances. Other fields, associated with nuclear forces, have very short ranges. These differences are not arbitrary. They arise from the properties of the fields themselves, such as whether their excitations have mass. A field whose disturbances are massless can influence the universe over vast distances, while a field whose disturbances are massive is confined to a narrow region. In this way, the reach of a force is encoded directly into the nature of its field. Another crucial insight is that interactions are inseparable from the concept of measurement. In quantum physics, to observe a particle is to interact with it. There is no passive observation. Measuring devices are themselves physical systems with fields and particles, and any measurement involves an exchange of energy and information through interactions. This means that what we can know about particles is limited by how they interact with our instruments. Feynman saw this not as a flaw, but as a defining feature of scientific knowledge. The field-based picture also clarifies why certain quantities are conserved. Energy conservation, for example, is not enforced by an external rule. It emerges naturally from the structure of fields that do not change with time. Momentum conservation follows from the uniformity of space. These principles are deeply woven into the behavior of fields, ensuring that interactions always balance in precise ways. The remarkable reliability of conservation laws across all experiments reflects the deep symmetry of the underlying fields. As physics advanced, the idea of fields expanded beyond electromagnetism. Each fundamental interaction is associated with its own field. Some of these fields are less intuitive because their effects are noticeable only at very small scales or high energies. Yet they are no less real. Their existence is confirmed by consistent experimental results, even if we cannot experience them directly in daily life. Feynman often stressed that direct sensory experience is a poor guide to fundamental truth. Experiments in mathematics provide a more reliable compass. One of the most challenging aspects of field theory is its treatment of infinity. When physicists first applied quantum ideas to fields, calculations produced infinite results, which seemed to threaten the entire framework. Rather than abandoning the theory, scientists developed methods to handle these infinities in a controlled way. Feynman played a central role in making these methods practical. The success of these techniques is another indication that fields capture something real about nature, even if our mathematical tools sometimes struggle to keep up. Interactions mediated by fields also reveal why the universe has structure at all. Without fields, particles would not bind together to form atoms, molecules, or larger systems. Fields provide the glue that holds matter together, but they also provide the resistance that prevents collapse. Stability emerges from a balance of interactions. This balance is delicate, yet remarkably robust, allowing complex structures to persist over enormous spans of time. At the same time, fields allow for change. Interactions can rearrange matter, transfer energy, and create entirely new particles. In high-energy environments, such as the early universe or powerful accelerators, fields interact in ways that produce phenomena far removed from everyday experience. Yet these extreme cases obey the same underlying principles as ordinary processes. There is no separate set of rules for the exotic and the familiar, only different regimes of the same field interaction. Feynman often highlighted the importance of imagination in working with fields, but he was careful to distinguish imagination from fantasy. Imagination in physics is disciplined by experiment. We are free to invent mathematical structures and conceptual models, but nature has the final say. Fields earned their place in physics because they consistently predicted new phenomena and explained existing ones better than any alternative description. Another deep implication of field theory is that it blurs the line between substance and process. A field is not a static thing sitting in space. It is an active participant in every interaction. Space itself becomes a stage rich with properties. This challenges the old notion of space as a passive container. Instead, space is filled with entities that can store energy, transmit influence, and respond dynamically to change. The field-based view also reshapes our understanding of identity. A particle's identity is not in essence hidden inside it, but a pattern of interactions. If a particle responds like an electron in every experiment, then it is an electron. There is no deeper question of what it really is beyond how it behaves. This pragmatic definition aligns with Feynman's insistence that physics concerns what we can say about nature, not metaphysical speculation detached from observation. Fields further provide a framework for unification. Interactions that appear distinct at low energies can merge into a single description at higher energies. This suggests that the variety of forces we observe may be different expressions of a more unified underlying field structure. While a complete unification remains a goal rather than an achievement, the field approach has consistently guided progress toward deeper connection. In practical terms, our modern world is built on an understanding of fields and interaction. Communication technologies rely on electromagnetic fields. Medical imaging exploits interactions between fields and matter. Even the stability of everyday materials depends on field-mediated forces. These applications are not accidental, they flow directly from understanding how fields govern interactions at the most fundamental level. Feynman's way of presenting these ideas stripped away unnecessary mysticism while preserving their depth. He encouraged curiosity without dogma, reminding us that fields are tools for understanding, not sacred objects. Their value lies in what they allow us to predict and explain. If a better framework someday replaces them, science will adopt it without hesitation. Until then, fields remain one of our most powerful ways of making sense of the universe. Ultimately, fields and interactions reveal a universe that is deeply relational. Nothing exists entirely on its own. Every particle is embedded in a network of influences that shape its behavior. Reality is not a collection of isolated entities, but a continuous interplay of fields interacting according to precise rules. This vision, so clearly articulated by Feynman, invites us to see the world not as a set of disconnected objects, but as a coherent, dynamic whole, where understanding arises from tracing the patterns of interaction that bind everything together. When Richard Feynman addressed quantum behavior and probability, he was confronting one of the most unsettling and revolutionary ideas ever introduced into science. At the smallest scales of nature, the universe does not behave in a way that matches everyday logic. The world of particles is not governed by certainty, smooth motion, or clearly defined paths. Instead, it is governed by probability, ambiguity, and rules that challenge the way human intuition has evolved to understand reality. In classical physics, if you know the position and speed of an object at one moment, you can predict where it will be at any future time. This idea worked remarkably well for planets, projectiles, and machines. For centuries, it shaped the belief that the universe is a vast clockwork mechanism, unfolding predictably once its initial conditions are known. Quantum physics shattered this belief, and Feynman made it clear that this was not due to a lack of knowledge or poor instruments, but because nature itself does not operate in a deterministic way at small scales. At the heart of quantum behavior lies the concept of probability. Particles do not have definite positions or paths until they interact with something else. Instead of asking where a particle is, quantum theory asks how likely it is to be found in various places. These probabilities are not guesses. They are calculated precisely using mathematical rules that have been tested countless times. What makes them strange is that they describe reality itself, not our ignorance of it. Feynman often explained this using simple but profound examples. If a particle travels from one point to another, it does not follow a single path. Instead, it behaves as if it explores every possible path simultaneously. Some paths contribute strongly, others cancel out, and the final outcome is determined by the combined effect of all possibilities. This idea is not metaphorical. It is built directly into the equations that accurately predict experimental results. Nature, at its core, does not choose one story in advance. It allows all allowed stories to contribute. This probabilistic behavior becomes unavoidable in experiments such as the famous double-slit experiment. When particles like electrons are fired one by one through two slits, they produce an interference pattern, a result that seems impossible if each particle were simply a tiny object choosing one slit or the other. The pattern emerges only when we accept that each particle behaves like a wave of possibilities interfering with itself. Yet when a particle is detected, it always appears as a single, localized event. This dual behavior defies classical categories. It is neither purely a particle nor purely a wave, but something fundamentally new. Feynman emphasized that attempts to force quantum behavior into classical pictures inevitably led to confusion. The problem is not that quantum theory is incomplete, but that our everyday concepts are inadequate. Nature does not care about our preferences for certainty and clarity. It follows its own rules, and our task is to learn how to work with them, not to replace them with more comfortable ideas. Probability in quantum mechanics is different from probability in everyday life. When we say there is a probability that it will rain tomorrow, we usually mean that we lack complete information about complex atmospheric conditions. In principle, with enough data and computing power, the outcome could be predicted exactly. Quantum probability is not like this. Even with perfect knowledge of a system, the theory provides only probabilities, not certainties. This randomness is built into the fabric of reality. Feynman was careful to stress that this randomness does not imply chaos. Quantum probabilities are governed by strict mathematical rules. The outcomes may be unpredictable individually, but their statistical patterns are highly ordered. When experiments are repeated many times, the results align with theoretical predictions with astonishing accuracy. Nature is unpredictable in detail, but reliable in pattern. Another deeply counterintuitive aspect of quantum behavior is the role of observation. In classical physics, observation simply reveals what is already there. In quantum physics, observation is an interaction that changes the system. Measuring a particle's position affects its momentum. Measuring its energy affects its timing. This is not due to clumsy instruments but to the structure of the theory itself. Certain properties cannot be simultaneously well-defined. This limitation is not a statement about human capability but about how nature works. Feynman resisted mystical interpretations of this fact. He rejected the idea that human consciousness plays a special role in creating reality. Instead, he emphasized that any interaction capable of extracting information counts as a measurement. The strange features of quantum mechanics arise not from observers being special, but from interactions being unavoidable. To know something about a particle, you must interact with it, and that interaction changes the system. Quantum behavior also undermines the classical notion of identity over time. A particle detected at one moment is not guaranteed to have a continuous history that can be traced backward in a simple way. Between interactions, the theory does not assign a definite story to what the particle was doing. It assigns a range of possibilities. Asking which one really happened is, according to Feynman, the wrong question. Physics concerns what can be predicted and measured, not imagined narratives that leave no experimental trace. This shift in thinking has profound consequences. It means that the universe is not a fixed script unfolding step by step, but a process in which multiple potential futures coexist until interactions select one outcome. This does not remove causality, but it softens it. Causes influence probabilities rather than dictating outcomes with certainty. The universe becomes less like a machine and more like a game governed by precise rules but unpredictable plays. Feynman acknowledged that this view is uncomfortable. Humans crave certainty and clear explanation. Quantum mechanics denies us both at a fundamental level. Yet he insisted that discomfort is not a valid argument against truth. The only question that matters is whether the theory works, and quantum theory works better than any other theory ever devised, predicting phenomena across an enormous range of scales with unmatched precision. Quantum probability also reveals a deeper unity between mathematics and nature. The abstract mathematical structures used in quantum theory are not convenient approximations. They appear to reflect how reality is organized. Complex numbers, probability amplitudes, and interference are not human inventions imposed on nature, but tools that nature itself seems to use. This realization blurs the line between description and reality, suggesting that the universe may be deeply mathematical at its core. At the same time, Feynman cautioned against turning quantum mechanics into philosophy detached from experiment. Its meaning lies in what it allows us to calculate and predict. Debates about what is really happening beyond measurable outcomes often generate more confusion than insight. The strength of quantum theory is its ability to connect abstract mathematics with concrete experimental results again and again. Quantum behavior and probability force us to rethink what it means to understand something. Understanding does not always mean reducing phenomena to familiar pictures. Sometimes it means accepting rules that work even when they resist visualization. Feynman encouraged embracing this kind of understanding, one that values predictive power and internal consistency over intuitive comfort. In this sense, quantum probability is not a weakness of our description of nature, but a window into its deepest structure. It tells us that reality is not built from certainties stacked upon certainties, but from possibilities constrained by strict laws. From these possibilities arise the stable patterns we observe at larger scales. The solid world, governed by seemingly deterministic rules, is an emergent consequence of underlying quantum uncertainty averaged over countless interactions. By confronting us with probability at the foundation of existence, quantum mechanics reshapes our view of reality itself. It teaches humility, reminding us that the universe is under no obligation to align with human intuition. It also teaches confidence, showing that even a strange and probabilistic world can be understood with extraordinary precision. This balance between mystery and clarity, so central to Feynman's approach, lies at the heart of quantum behavior and remains one of the most profound insights science has ever achieved. Continuing deeper into quantum behavior and probability, one of the most striking realizations is that chance is not merely tolerated by nature, it is required. At the quantum level, randomness is not an accident or a flaw in the laws, it is an essential feature. If quantum events were fully predictable, many of the structures that make the universe stable would not exist. The apparent solidity of matter, the stability of atoms, and the reliability of chemical bonds all depend on quantum uncertainty playing its role in exactly the right way. Feynman often emphasized that quantum probability is not a retreat for explanation but a refinement of it. Instead of asking for a single outcome, physics asks for the distribution of outcomes. This shift may seem like a loss, but it is actually a gain. Probability allows us to describe systems that would otherwise be impossible to explain. The behavior of electrons in atoms, for example, cannot be captured by fixed orbits without contradicting experimental evidence. Probability waves provide a consistent and testable description that explains why atoms have specific sizes and energies. Another crucial feature of quantum probability is interference. Probabilities in quantum mechanics do not simply add, they interfere. Possibilities can reinforce or cancel one another, leading to outcomes that have no classical counterpart. This interference is the key to understanding why certain events are allowed and others are suppressed. It is also the reason why quantum mechanics cannot be reduced to classical probability theory. The rules governing quantum probabilities are fundamentally different and richer. Feynman's formulation of quantum mechanics made this point especially clear. By summing over all possible paths, the theory assigns each path a contribution, and the final probability emerges from the combination of these contributions. This approach does not privilege one path as the real one. All contribute, and the observable outcome reflects their collective effect. Asking which path the particle actually took misses the essence of the theory. The question has no answer because nature does not select a single path until an interaction forces an outcome. This perspective has deep implications for how we think about reality between observations. Classical intuition insists that something definite must be happening at all times. Quantum mechanics challenges this insistence. Between interactions, the theory provides a complete description in terms of probabilities, and nothing is missing. There is no hidden story waiting to be uncovered. Feynman argued that the demand for such a story comes from human habits of thought, not from experimental necessity. Quantum probability also reshapes the idea of cause and effect. Causes do not determine exact results, they shape probability distributions. If you prepare a system in a certain way, you do not fix what will happen, but you fix what is likely to happen. This weaker form of causality may feel unsatisfying, but it is precisely what experiments confirm. The universe respects causes, but it does not guarantee outcomes. At larger scales, this probabilistic causality blends into the apparent determinism of everyday life. When enormous numbers of quantum events are involved, fluctuations average out, and probabilities become near certainties. This is why classical physics works so well for macroscopic objects. Determinism is not fundamental. It is an emergent approximation. Feynman delighted in pointing out that classical certainty is a statistical illusion arising from quantum uncertainty. Another profound implication is the impossibility of complete prediction. Even with perfect preparation and flawless instruments, there will always be aspects of future events that cannot be foretold. This does not mean that nature is irrational or lawless. On the contrary, the laws are what limit and shape the randomness. Quantum mechanics tells us not what will happen, but what can happen and with what likelihood. This is a subtler and more flexible form of lawfulness. Quantum probability also explains why certain transitions are forbidden. Some events simply never occur, not because they are improbable, but because the probabilities cancel out exactly. These forbidden processes reveal hidden symmetries and constraints in the laws of nature. The absence of certain outcomes is just as informative as the presence of others. In this way, probability becomes a powerful diagnostic tool, revealing structure through both occurrence and non-occurrence. Feynman was careful to distinguish acceptance from resignation. Accepting quantum probability does not mean giving up on understanding. It means understanding on nature's terms. Once the rules are accepted, quantum mechanics becomes an extraordinarily clear and precise framework. Calculations lead directly to predictions, and those predictions match reality with uncanny accuracy. The mystery lies not in the theory's performance, but in its departure from intuition. This departure also affects how we think about explanation in general. An explanation need not provide a picture that can be imagined. It must provide a rule that can be applied. Quantum mechanics excels at this. It tells us how to calculate outcomes, how to test predictions, and how to refine our understanding. The fact that the underlying processes resist visualization does not diminish the theory's explanatory power. Quantum probability further dissolves the boundary between necessity and chance. Events are neither fully necessary nor fully accidental. They occur within a structured space of possibilities defined by physical law. This blend of order and unpredictability is one of the most profound features of the universe. It allows for creativity, novelty, and diversity while maintaining overall stability. In technological terms, embracing quantum probability has led to revolutionary advances. Lasers, semiconductors, medical imaging, and emerging quantum technology all rely on precise control of probabilistic quantum behavior. These technologies do not fight quantum uncertainty, they exploit it. This practical success is a strong argument that quantum probability reflects something real about the world, not just a limitation of human knowledge. Feynman often remarked that the deepest lesson of quantum mechanics is intellectual humility. Nature is stranger than we imagine, and perhaps stranger than we can imagine. Yet it is also accessible through careful experiment and honest mathematics. We do not need to fully visualize quantum behavior to use it effectively. Understanding, in this context, means knowing how to work within the rules that nature provides. In the end, quantum behavior and probability reveal a universe that is neither rigidly deterministic nor chaotically random. It is a universe governed by precise laws that define possibilities rather than certainty. From this foundation emerges the stable, predictable world we experience, built from countless quantum events, averaging into reliable patterns. This vision, so powerfully articulated by Feynman, invites us to accept uncertainty not as ignorance, but as a fundamental feature of reality itself, one that deepens rather than diminishes our understanding of the universe. When Richard Feynman explained forces as exchanges rather than simple pushes and pulls, he transformed one of the oldest ideas in physics into something far more precise and revealing. In everyday experience, a force feels like direct contact or influence. You push a table, and it moves. You pull an object, and it follows. This intuition encourages the belief that forces are continuous actions exerted directly between objects. At the fundamental level, however, nature works differently. Forces arise from interactions mediated by particles, and it is the exchanges that give rise to attraction, repulsion, and motion. In this picture, No particle reaches out across empty space to grab another. Instead, particles interact by exchanging quanta of fields. The electromagnetic force, for example, is understood as the exchange of photons between charged particles. These photons are not always visible as light. Most of them are virtual, meaning they exist only during the interaction and cannot be directly observed. Yet their effects are real. They carry energy and a momentum, and their exchange alters the motion of the particles involved. Feynman emphasized that these exchange particles should not be imagined as tiny balls flying back and forth like ping-pong balls. They are mathematical elements within a theory that allow us to calculate probabilities accurately. What matters is not their physical appearance, but the role they play in interactions. The language of particle exchange provides a compact and reliable way to describe how forces operate at the quantum level. This idea unifies forces and particles into a single framework. Matter particles and force particles are not fundamentally different kinds of things. They are all excitations of fields. Some fields give rise to particles that make up matter, while others give rise to particles that mediate interactions. The distinction is one of role, not of substance. This realization dissolves the sharp boundary that once separated things from forces. Understanding forces of exchanges also explains why forces have specific strengths. The probability that an exchange occurs and the way it alters motion depends on the properties of the particles involved and the rules governing their interaction. These rules are encoded in mathematical constants that experiments measure with extraordinary precision. The apparent strength of a force is a reflection of how likely certain exchanges are and how they influence the behavior of particles. Another important consequence of this view is that forces are inherently quantum. They do not act smoothly and continuously at the smallest scales, but through discrete interaction events. When two electrons repel each other, the repulsion arises from countless tiny exchanges that, when averaged together, produce a smooth force at larger scales. What feels continuous to us is, at its foundation, a rapid sequence of quantum interactions. Feynman diagrams provide a powerful way to visualize and calculate these exchanges. Each diagram represents a possible interaction process, showing how particles exchange quanta and change their states. These diagrams are not literal pictures of reality, but bookkeeping tools that encode the mathematics of interaction. Their success lies in how efficiently they organize complex calculations and connect theory directly to experimental results. The exchange picture also clarifies why forces obey conservation laws. When particles exchange quanta, energy and momentum are transferred in precise amounts. Nothing is lost or gained mysteriously. Every interaction balances exactly, reflecting the deep symmetries of the underlying laws. Conservation is not imposed from outside. It is built into the exchange process itself. Perhaps most striking is how this framework extends beyond electromagnetism. Other fundamental forces are also described by particle exchanges, each with its own characteristic mediators and behavior. Some exchanges act over long distances, while others are confined to extremely short ranges. These differences arise naturally from the properties of the exchange particles, not from separate principles for each force. By framing forces as exchanges, Feynman helped replace vague notions of action with a concrete and testable mechanism. Forces are no longer mysterious influences but predictable outcomes of interaction rules. This perspective does not remove wonder from physics, it deepens it. From the silent exchange of invisible quanta emerges the motion of planets, the structure of atoms, and the stability of matter itself. When Richard Feynman spoke about symmetry and simplicity, he was pointing to one of the most quietly powerful ideas in all of physics. At first glance, the universe appears overwhelmingly complex. There are countless kinds of matter, endless forms of motion, and an enormous variety of phenomena. Yet beneath this surface complexity lies a surprising simplicity, governed by deep symmetries that shape how particles exist and how they interact. These symmetries are not decorative patterns. They are the backbone of physical law. Symmetry in physics does not mean visual beauty or mirror images alone. It means invariance, the idea that certain features of nature remain unchanged even when we change our perspective. If the laws of physics work the same today as they did yesterday, that is a symmetry in time. If the same experiment gives the same result here as it does on the other side of the universe, That is a symmetry in space. Feynman emphasized that these simple statements carry enormous consequences. One of the most profound discoveries in modern physics is that every fundamental conservation law is linked to a symmetry. Energy conservation arises because the laws of physics do not change with time. Momentum conservation exists because the laws are the same everywhere in space. These are not coincidences, they are expressions of deep order. Symmetry is not something added to nature, it is something nature demands. At the level of particles, symmetry determines what is allowed and what is forbidden. Certain particles exist because the underlying laws permit them, while others cannot exist because they would violate symmetry principles. Even the properties of particles, such as charge and spin, are tied to symmetrical structures in the equations that describe fields. What seems like a long list of unrelated facts about particles is actually the visible consequence of a much smaller set of organizing principles. Feynman delighted in showing how apparent complexity emerges from simple rules applied repeatedly. When many particles interact according to the same symmetrical laws, the result can look chaotic or intricate, even though the underlying instructions are minimal. This is similar to how simple mathematical rules can generate complex patterns, or how a few basic notes can produce an entire symphony. Complexity is not evidence of complicated laws. It is often evidence of simple laws acting at scale. Symmetry also explains why nature is economical. Instead of inventing a new rule for every situation, the universe uses the same principles again and again. The same electromagnetic interaction governs lightning in a storm, chemical bonds in a molecule, and signals in the brain. This reuse is not accidental. It reflects a deep simplicity in the structure of physical law. Once the rules are set, everything else follows. Another important aspect of symmetry is that it guides discovery. Physicists often predict new particles or interactions not because they have been observed, but because symmetry requires them. When experiments later confirm these predictions, it reinforces the idea that symmetry is not just a descriptive tool, but a creative force in understanding nature. Feynman appreciated this predictive power while remaining cautious, always insisting that experiment has the final word. Symmetry also brings clarity to what might otherwise seem arbitrary. Why do particles have the charges they do? Why do interactions have specific strengths? Many of these questions find their answers not in complicated mechanisms, but in symmetrical constraints. The laws could have been Messier, but they are not. Nature appears to prefer balance and consistency over excess. At the same time, symmetry can be hidden. The universe we observe does not always look symmetrical. Left and right can behave differently in certain interactions, and some processes break symmetries that seem fundamental. Feynman stressed that broken symmetry is not a failure of simplicity, but a refinement of it. The underlying laws may be symmetrical, even if their outcomes are not. This idea explains how diversity and structure arise from uniform beginnings. Simplicity, in Feynman's view, was never about making things easy. Simple laws can produce behavior that is extremely difficult to predict in detail. What matters is not how complicated the outcome looks, but how few assumptions are needed to describe the rules behind it. True simplicity lies in the foundations, not in the surface appearance. Ultimately, symmetry and simplicity offer a powerful lesson about understanding the universe. Nature is not an accumulation of unrelated facts, but a coherent system governed by a small number of principles. By uncovering these principles, physics turns confusion into clarity without diminishing wonder. The universe remains rich and surprising, but it is not arbitrary. Beneath its endless variety lies an elegant order, quietly shaping everything that exists. When Richard Feynman spoke about experiments as the ultimate judge of what particles really are, he was defending the core discipline that keeps science honest. No matter how elegant a theory may appear, no matter how convincing a mathematical argument sounds, it must answer to nature itself. In particle physics, where the entities involved are far removed from direct human experience, experiments are not just helpful, they are essential. Without them, particles would remain abstract ideas rather than reliable descriptions of reality. Particles are not discovered by imagination alone. They are inferred from patterns in experimental results. Tracks in detectors, flashes of light, tiny electrical signals. These are the clues from which physicists reconstruct the behavior of invisible entities. Feynman emphasized that what we call a particle is defined by how consistently it produces certain experimental signatures. If the same patterns appear again and again under controlled conditions, we conclude that something real is responsible for them. This approach guards against self-deception. History is full of beautiful theories that failed because they did not match experiment. Feynman reminded students that it does not matter who proposed a theory or how clever it seems. If its predictions disagree with observation, it is wrong. This uncompromising standard is not harsh. It is what allows science to progress. Each failed idea clears the way for a better one. Experiments also reveal surprises that theory alone would never predict. Many particles were discovered not because someone expected them, but because experiments produced unexplained results. Instead of forcing data to fit existing ideas, physicists had to expand their theories. This openness to surprise is a defining feature of experimental science. It acknowledges that nature is under no obligation to align with human expectations. In particle physics, experiments often push technology to its limits. Accelerators, detectors, and data analysis methods are designed to probe scales far beyond everyday experience. Feynman admired this ingenuity, seeing it as a natural extension of curiosity. By creating extreme conditions, experiments reveal aspects of particles that would otherwise remain hidden. Each improvement in experimental capability opens a new window onto reality. The role of experiment is not only to confirm theories, but to define the questions worth asking. Some theoretical possibilities remain untestable with current technology, and Feynman cautioned against giving them too much weight. Science advances most effectively when theory and experiment move together, each guiding and correcting the other. Experiments anchor speculation to reality. Another important point is that experiments do not speak for themselves. They require interpretation, careful analysis, and an understanding of uncertainty. Feynman emphasized honesty in this process. One must report results accurately, including errors and limitations. Overstating conclusions or ignoring inconvenient data undermines the entire enterprise. Scientific integrity depends on acknowledging what experiments truly show, not what one wishes they would show. Repeated experiments play a crucial role in establishing what particles are. A single observation is rarely enough. Consistency across different setups, energies, and methods builds confidence that a result reflects a genuine feature of nature rather than an experimental artifact. This redundancy is not wasteful, it is the foundation of reliability. Experiments also help refine concepts. Early ideas about particles often changed as new data emerged. Properties once thought fundamental turned out to be emergent or approximate. This adaptability is a strength, not a weakness. It shows that scientific knowledge is provisional, always open to improvement as evidence accumulates. Feynman viewed experiments as conversations with nature. Each experiment asks a question, and nature answers in its own language. The scientist's task is to listen carefully and translate that answer into understanding. Misinterpretation is always possible, which is why skepticism and repetition are vital. In the end, experiments ground particle physics in reality. They ensure that particles are not metaphysical speculations but practical tools for explaining the world. Through experiment, invisible entities become part of a tested framework that connects mathematics, observation, and prediction. This disciplined reliance on evidence is what allows particle physics to move confidently into realms far beyond direct human perception, while remaining firmly anchored in truth. When Richard Feynman spoke about why particles matter for understanding the universe, ourselves, he was reaching beyond technical physics into a broader vision of knowledge. Particles are not important merely because they are small or exotic, but because they provide a common foundation for explaining phenomena across every scale of existence. By understanding particles, we gain insight into how the universe is organized and how complex structures, including life and thought, arise from simple rules. Particles matter because they unify our explanation. The same fundamental entities and interactions that govern distant galaxies also govern the chemistry of cells and the electrical activity of the brain. There is no separate set of laws for living things and non-living things. This continuity is one of the most powerful messages of modern physics. It tells us that we are not outsiders in the universe, but expressions of the same principles that shape stars and atoms. This perspective reshapes our sense of place. Humans often imagine themselves as detached observers of nature, studying a world that is fundamentally different from them. Particle physics dissolves this separation. The atoms in our bodies obey the same rules as atoms anywhere else. The energy flowing through our nervous systems follows the same laws as energy in a lightning bolt or a distant supernova. Understanding particles is, in a literal sense, understanding ourselves. Feynman emphasized that this does not reduce human experience to something trivial or mechanical. Knowing that music is made of sound waves does not diminish its beauty. Similarly, knowing that life emerges from particle interactions does not strip it of meaning. Instead, it adds depth. It reveals that meaning and complexity are not imposed from outside nature, but arise naturally within it. The universe has the capacity to produce beings who can reflect on its workings. Particles also matter because they explain stability and change, the long-term persistence of matter, the reliability of chemical reactions, and the slow evolution of biological systems all depend on the consistency of particle behavior. At the same time, particles allow for novelty. Random quantum events introduce variation, while interactions shape outcomes. This balance between order and chance makes evolution, creativity, and adaptation possible. Another reason particles are central is that they connect the abstract and the practical. Theoretical insights about particles have led directly to technologies that define modern life. Electronics, medical diagnostics, energy production, and communication systems all rely on precise control of particle behavior. These applications are not accidental spin-offs, they are direct consequences of understanding how the universe works at its most basic level. Feynman often pointed out that studying particles teaches intellectual humility. The deeper we probe, the more we encounter phenomena that defy common sense. This challenges us to let go of comfortable assumptions and accept that reality may be stranger than intuition suggests. At the same time, particle physics demonstrates the power of human reason. Even a strange and counterintuitive world can be understood through careful experiment and clear thinking. Particles also influence how we think about explanation and knowledge. They show that understanding does not always mean finding a familiar picture. Sometimes it means accepting abstract rules that nonetheless yield accurate predictions. This lesson extends beyond physics. It encourages a flexible and evidence-based approach to understanding in any field. On a philosophical level, particles invite reflection on unity and diversity. A small set of fundamental entities gives rise to an immense variety of forms and behaviors. This suggests that complexity does not require complex origin. Simple rules, applied consistently, can generate richness beyond imagination. This insight resonates far beyond physics, offering a general principle for understanding complex systems. Feynman saw science not as a collection of facts, but as a way of thinking. Studying particles cultivates this way of thinking by demanding precision, skepticism, and openness to surprise. It trains us to test ideas against reality and to revise beliefs when evidence demands it. These habits are valuable not only in laboratories, but in everyday life. Ultimately, particles matter because they connect the human story to the cosmic story. They show that the same universe that produced galaxy also produced curiosity, creativity, and consciousness. In understanding particles, we do not step away from what makes us human. We deepen it. We learn that we are part of a universe governed by understandable laws, yet rich enough to contain mystery, beauty, and meaning.